So let's talk about the interior of the sun. But actually, before that, let's kind of put some labels on what we see, and what its structure is, what its geometry. Basically, it's a ball of gas. So basically, a sphere with a radius that is 109 times the radius of the Earth. So basically, it takes about 100 Earths to fill up the sun's diameter, like beads. On a string. Does it make sense? Missed one here, right? So Earths. And actually, that is quite the size, right? So this size of Earth. All right. Of course, this is not just diameter, so it's going to take, and we can calculate that, but you don't have to. It takes about 300,000 Earths to fill out the whole sphere of the sun. It's definitely very luminous, so that's a lot of powers. Just to make sure, this is to the power of 26 watts, so about 4 times 10 to the 26. We don't even have a number, a name for that, like billions of billions of billions, and then you get the 10 to the 26. Okay, and here's another thing about the sun. It does rotate, right? So basically, every 30 years, right? Every 30 days, you're gonna, if you monitor the sun, if you look at the sun, obviously through a specialized solar telescope, you're gonna see the kind of the freckles on the surface of the sun kind of move like this. Okay, and it's gonna take roughly 30 days for that sunspot, if it's going to survive, to kind of come back, right? So yeah, it's gonna move every day like this, so we can observe that rotation. That's observable. These freckles, we're going to talk about them later. They are sun spots, and I'm not going to divulge now what they are. You're going to have to watch the next lecture for that. All right, so the structure of the sun. We're going to start with the outermost layer, the solar wind, which is basically a wind of a flow of charged particles from the surface of the sun. And it's very important. So all these come and they meet a planet like Earth that rotates, and it has magnetic field, and it creates a magnetosphere. It kind of goes like this. And this magnetosphere keeps us safe from other charged, very energetic particles out there. So this was Earth as an example. All right, so helps shape the magnetic field of planets, and also forms the comet tail. So you have the wind, right? And then a comet comes in its orbit towards the sun. So say the orbit is like this. So if it's coming in this way, it's going to have the tail in the direction opposite to the wind. So if this is the wind, then this is going to be the tail of the comet. Okay, the comet will go like this, but of course because of the wind, the tail will be created that way. It's always in the direction of the wind. All right, so this is basically the outermost shell. Let's go towards the interior of the sun, and we are going to meet the next layer that is called the corona. Okay, this is basically the outermost layer of the solar atmosphere. You would say, well, what's an atmosphere? Well, it's something that is above the layer that we can consider the surface. We're going to get to it in a second. We cannot see the corona with our eyes because our eyes do not see in X-rays, and because that corona is so hot. And then if you apply Wien's law, you find out that the wavelength, remember, that goes like 1 over temperature, the wavelength that 1 million degrees plasma basically it's going to emit its maximum intensity in X-rays. So it's very hot, but it's very, very low density. So basically, as a consequence, there is very little heat. You basically get hit by one of those charged particles, charged and very energetic particles, every once in a while. All right, so very little heat. All right, let's move inward. Going to meet the chromosphere, right? So we had something like that, so now we're here. Chromosphere. This is what you should imagine about that layer. That's the middle layer of solar atmosphere. So the temperature, it's 10 to the 4 to 10 to the 5, right? So for those of you still not used to the powers of 10, that's tens of thousands to hundreds of thousands of Kelvin. And again, Wien's law that links the wavelength with the temperature reveals to us that that layer of the sun radiates with ultraviolet light. Okay, inward some more, and we get to see the visible surface of the sun, or the photosphere. And in average, the temperature is around 6,000 Kelvin. Okay, so this is still, right, it does seem to be like a surface, but it's not a hard thing. It's still just a layer of gas. It's still only hydrogen and helium. 98%. It's only 2% of the interior of the sun that is something else, like carbon, nitrogen, all other heavier elements. Okay, so yeah, just a reminder that the sun is basically a ball of hydrogen and helium. And so even though it feels like the surface of the sun, it is much less dense than the Earth's atmosphere. Okay, so it's very, very rarefied medium, if you want. Okay, moving on. Inside the photosphere, we are going to find the convection zone. So this is going to be this, where you see these convection cells. And this is what happens, this transport of energy that uh, basically means there is some upward rising of the hot gas and downward falling of the cool gas. The cool gas cascades down. All right, so it makes up for about 30% of the outer layer of whatever is interior to the photosphere. Even more inward, so basically interior to the convection zone, now we are going to meet the radiation zone. So it's basically from here to here, and you're gonna see here lots of photons that are moving around, scattered. They take actually a lot of time to escape. They're produced in the core, and after that they actually dance a lot before they make it into the convection zone and then the photosphere, chromosphere, and so on. So it's a much calmer plasma here. All right, so this is where the energy is transported upward by photons, but very, very slowly. It takes hundreds of thousands of years for a photon, for photons to escape this radiation zone. Very hot. Those photons are not there for nothing. They stay there. They keep their energy with them. And so again, we're talking about millions of Kelvin. Wien's law is going to tell us that that portion of the sun emits in the X-ray, and it's pretty vast portion of the sun accounts for that radiation zone. So it's basically the inner 70% of the sun. Arrived at the very center, obviously the core of the sun, and this is where the energy is generated, is created, and that's created by nuclear fusion. So yes, millions of Kelvin, but a bit higher, okay? And that's actually where gamma rays are produced, and they cool off a little bit and they become X-rays here. But this is where there are the nuclear reaction that produce the gamma rays, the hottest photons of light that we know of. Very high pressure. It's basically 200 billion times the pressure of on the Earth's surface. So yeah, you definitely don't want to be there. So I guess that's about it. That's it. So we go from core, right? So if this is the radius of the sun, we go from core to somewhere here is going to be radiation zone, followed by the convection zone, and then the next layer is going to be photosphere, and then the next one is going to be chromosphere, and above the chromosphere is corona, and above that the solar wind. Okay, so increasing radius. Somewhere here the sun ended.